Good evening, good morning, and good afternoon. Hope you are all doing well and staying safe. I'm Mariam Shref, a senior petroleum engineering student at the Lebanese American University, and I'll be moderating today's session. So it's my pleasure on the behalf of PeoPetro to welcome you all to the second lecture of the online course Hydraulic Fracturing, which has been presented by a special distinguished speaker, Dr. Mohamed Soliman. I'm sure his participation with us today will benefit all participants. With that, I advise you to give your full attention to this informative session today. So let me begin by reintroducing our guest speaker for today, Professor Soliman. So Professor Soliman is the chairman of the Petroleum Engineering Department at University of Houston. Dr. Soliman has a long industrial and academic experience. He holds 35 patents on fracturing operations and analysis, testing, and conformance applications. He is the author and co-author of over 250 technical papers and articles in various areas of petroleum engineering. Dr. Soliman is a registered professional engineer in the state of Texas. He is also a distinguished member of the Society of Petroleum Engineers and fellow of the National Academy of the Inventors. To highlight, he has authored several book chapters on stimulation and testing. Additionally, he is the primary editor of Fracturing Horizontal Wells, published by Macro-Hill in 2016. He is also the co-author of Optimization of Hydraulic Fracture Stages and Sequences in Unconventional Formations, published in 2018 by CRC. Finally, Dr. Soliman holds a Bachelor of Science with top honors from Cairo University and a Master's and a PhD degree from Stanford University.
Thank you everyone for attending. Thank you, Mariam, for the introduction. Thank you, Ahmed, for arranging this teaching, giving me more work to do than I, as if I don't need any more work. Anyway, this is the second lecture. We talked last week about history of hydraulic fracturing. I should have also mentioned last week that Mr. Buddy McDaniel is an old friend of mine and a colleague that we did a lot of work together, was the biggest contributor to the writing on fracturing, history of fracturing, fracturing was both vertical and horizontal. So if you, when you read this presentation, please remember that I should have acknowledged him as very knowledgeable person that we did a lot of work together. Last week, I also talked about fluid flow, and I mentioned the pseudo-radial flow and elliptical flow. So what I did, I'm having another 4 slides here to show you some numerical simulation of how the fluid flow would look. Just a simple case where I have a vertical hydraulic fracture in a formation and make it penetrating the whole formation to show you how the fluid flow would look. I'm showing a couple of illustrations. There will be 2 slides on infinite conductivity fractures and the 2 full slides on finite conductivity fractures. So here I'm saying CFD, and if you remember the definition of CFD, which is permeability of the fracture times the width of the fracture divided by formation permeability, and also divided by fracture half length, one wing of the fracture. And here I have very tight gas formation. So it takes, so the conductivity basically infinite, infinite meaning that the pressure drop inside the fracture is negligible relative to the pressure drop inside the formation. And you can see here, the behavior looks very much as if I have just a line inside the formation. That's what will give me linear flow. After a long time, you can see the pressure drop around the formation is demonstrated here. If I look at the outer boundary where the pressure has been significantly affected, You know, the rest, to the red one, the red area, basically saying we have not affected this area at all. So nothing coming out of, or very, very little coming out of this red area. Most of the fluid is coming out from this affected area. And you look at the affected area, it's elliptical shape, but it looks almost like a circle. So it is almost radial flow, and this is the reason you call it pseudo-radial flow. If I have finite conductivity fracture, you can see the effect is not as strong, and you don't see the end of the fractures right away. So it takes some time to see the end of the fracture. That is the bilinear flow. If you remember, we talked about that a little bit. And you can see with time, you end up seeing further and further into the formation, but the elliptical behavior is more dominant here till eventually you reach the pseudo-radial flow. Pseudo-radial flow, which is almost radial flow. It is still kind of elliptical. However, the major and minor axes of the ellipse are almost equal. If they are almost equal, so they are almost having radial flow. So that's the reason you would call it pseudo-radial flow. Fracturing, part of it is fluid flow. So we discussed that. Today we want to talk a little bit about rock mechanics and in situ stresses. Next week we'll talk about fracture mechanics, and last week we'll talk about testing. And please remember, that this is very introductory. You know, we don't go in things in huge details. We teach a graduate class I taught it in Texas Tech, and we'll teach it here at UH, where we go into all those areas in a lot more details and theory. So it is over 16-week, 3 hours per week, and homework and midterms and all kind of things. So let us talk a little bit about rock mechanics, because that's what we need to understand just before we get into the stresses. So what is rock mechanics? Basically, it is a discipline that you use to describe the behavior of underground formation and rock under in situ stresses, or sometimes externally applied loading conditions. That's what you do in hydraulic fracturing. And when you couple the fluid and the rock mechanics together, that's when you talk about geomechanics. And we'll be talking about both in the rest of the hour. Is it important to study rock mechanics and geomechanics in petroleum industry? Absolutely. Unfortunately, it has been ignored for a long time in teaching undergraduate and graduate classes, and that's a mistake, because it's important in drilling, borehole stability, what happened as you drill. We'll mention a few little things as we talk here. Formation breakdown, if your downhole pressure or the wellbore pressure, if it's too high, you could fracture the formation. If it is too low, you could collapse the wellbore. So it's very important to understand all this relationship in rock mechanics and the fluid flow. Stimulation obviously is very important. Fracture initiation pressure, we are going to look at one equation here. We spend a little bit of time on it for fracture initiation pressure, because it's very important to understand. Then next week we'll talk more about the fracture propagation pressure. To initiate the fracture requires certain pressure. It's going to be a little high pressure. People observe that. Once you fracture the formation, then your propagation will be at a lower pressure, but you can pressure that can be increasing with time, and one has to be able to analyze that propagation pressure. So we'll be talking about that both next week as well as in the testing part. And then all of that related to fracture geometry and designing of a fracture. That's all important. Then you get into production, and then there is a lot of aspects in rock mechanics, failure of the formation, sanding. We're not going to get into sanding at all in this course because it's more hydraulic fracturing. But sanding is very important, and we in a graduate class we end talking about sanding, the onset of sanding, and the calculation of how much sand you produce. You want to talk about some of the assumptions we work with. We can say, well, formation, many times, especially when you study well testing, they tell you homogeneous, the formation is homogeneous and isotropic. There are two different things. Homogeneous formation means that if you take one element in the formation, it's basically represented the whole body as the whole formation. That's a little different for being. So many of the formation we look at, many of the assumptions we make is the formation is homogeneous. Really, if you look at the formation at a very small element, they're really not homogeneous, but it is distributed so much that many of the formation, they behave as if they are homogeneous formation. So we'll look at some of this. Hopefully we can spend more time on it, because some of heterogeneities can be very important. When you get into heterogeneous formation, such as dual porosity shale, carbonate formation, this have a very strong effect on fracture propagation. We deal with it a lot in our work, especially when you get into shale formation and when you analyze data. Isotropy, whether you call formation isotropic or anisotropic, that means a dependence on direction. So a formation may be isotropic and homogeneous, it may be anisotropic and homogeneous. So if I have a formation that is, say, permeability in one direction is different from the other, so it can be homogeneous, but it's still anisotropic. Isotropic would mean that properties in various directions are the same. Now, when you talk about rock mechanics, many times we make the assumption that the formation is linearly elastic. Basically, linearly elastic is as if you're looking at a spring. So you push the spring down, you compress it, you relax, it goes back to original shape. So, and we'll describe it a little bit more detail mathematically in a minute. But basically, all we're saying here is the formation will disappear once you remove the external forces. So how realistic they are, essentially, I talked about that. Homogeneity many times is good assumption unless you get into a dual porosity or natural fracture formation, or it becomes important. We are going to see that the importance of heterogeneities when you talk about fracture design, and especially when you talk about analysis. When I get into analysis, I will show you something that we have been doing, and especially for shale formation, that heterogeneities have to be considered. The presence of natural fractures will have to be considered, which makes the formation heterogeneous. Isotropy, usually in a horizontal plane, it may not, properties may not vary very much, but we many times we assume isotropy, but you are going to see in testing again, and even in design, it can have an effect. Linearly elastic material, if we have hard rock, and we'll talk more definition of what hard rock is. If we have hard rock like sandstone, then the behavior would look very much like linearly elastic. But if you get a soft rock, such as when we fracture in the Gulf of Mexico, and I'm sure in areas where you live and you work. So in Gulf of Mexico, they are soft rock, so the behavior is different. It cannot be exactly considered linearly elastic. So there is other ways to handle that behavior. So if I look at it, when I say, and will be more of this in a minute, when I say linearly elastic, if I plot stress versus strain, and we'll talk about this in more in a few minutes. If I increase the stress, I get more strain. So basically, it is like if I have a core and I compress it, very much as if I'm compressing. You look here on the left-hand side, as if I'm compressing a spring. So if I compress it, it gets shorter, and then I release it, goes back to original value. And if you look at here, stress versus strain, so it's going in a straight line. If I release it, it goes back on that straight line. So not only this is linearly elastic, but there is no hysteresis. So it goes back on the same line. Does it always work this way? No. But this is a simplification that many people use. In reality, it may look like the curve we have here beside it, and that early part of behavior, which is an elastic strain, we used in some special testing. Unfortunately, I'm not going to get into that even in the testing part. It's too specialized. But we have used it many times. When we get to testing, we may be able to say a word or two about it. So eventually, in any of those curves, if you've studied material science, they will tell you, after some time, if your stress gets too high, the formation may fail. So you can have failure of the formation. That's a plastic behavior, so it cannot be reversed. Poor elasticity is very important concept to understand, where it affects the fracture, affects the rock behavior, and we'll talk more about it in a few minutes. For example, here, we're having two straight lines showing whether it is drained, same like the one above, stress versus strain. I probably should have defined what stress is. Stress is, have the units like pressure, is psi, force per unit area. However, it is not the same as pressure. Pressure usually is used to describe fluids. So pressure is a scalar quantity. Stress is a vectorial quantity, meaning that it has orientation. We'll see that in a minute. So I can, here I'm saying whether the rock does not have any fluid in it, it will follow different curve or different line than if it has fluid on it. And then we'll talk about stiffness versus frequency. We'll get into that in a little bit, because we can sometimes measure the behavior of the rock using a sonic lab or seismic or what one would call a static behavior, basically like what we are seeing here. So, what are the important parameters that you want to look at? The most important parameters for elastic properties you want to look at are Young's modulus, Poisson's ratio, and Bytes constant. And we'll talk a little bit about each of those. For stresses, I want to look at the total and effective stress. So keep that in mind. I will describe each one of them in a minute. So when I look at stress, if I have a piece of rock like what I have on the left, and I'm having stress, and you can see that I have a force, the force has an orientation. That can be, I can break it into its two main components, very much like what you study in math. So I can break this this force in two components, one parallel and one perpendicular to the rock. So the parallel one is my shear force, and here is the perpendicular one is normal force. So if I take that normal force divided by the area, that gives me the stress. That would be my normal stress. The shear stress is again the same thing. Take the parallel force divided by the area. So if I look at a piece of rock, you look at that nice looking graph. If I have a piece of rock downhole many hundreds or thousands of feet deep, it's exposed to stresses in all directions. It's not only in one direction, it's exposed to stress in all directions. But you can break those stresses into three principal stresses. If you study electrical engineering, you remember the right-hand rule and left-hand rule. So they have three, you break those stresses into three perpendicular stresses, and you call them three principal stresses. So they're all perpendicular to one another. Usually one is vertical and two are horizontal. In some cases, there may be some orientation to it. You know, if you're beside a mountain, you know, like near the Himalayas, near the Andes mountain, here in the United States, near mountains, these things will change. We'll talk about that in a minute. But you break the stresses into three perpendicular stresses, a vertical and two horizontal. So I will call that SV. That's my total stress. So that's vertical stress. The two horizontal stress, one usually is bigger than the other. So I'm going to call them SH max and SH min. And then your fluid will have a pressure. So there is a pore pressure inside the pores, because we don't have completely solid. So there's pores inside, and this will have pore pressure. Well, it's important to think about that. And then you have also the compressive strength of the rock, which is the unconfined compressive strength is the stress that will cause the rock to fail under compression when it is completely unconfined. You call that unconfined compressive stress. And you have the tensor strength of the rock. We talked about that last week. The one thing you have to remember, like anything in nature, you move from one point to another. You want to use, or you want to follow the path of least resistance. So if you are sitting at home, you want to go out, the path of least resistance to get out of the door, you go down the stairs, and so on and so forth. The same thing with fracture. It has to follow the path of least resistance. What is the path of least resistance for the formation, for a fracture to go? You can see if I have three stresses, the fracture will have to become perpendicular to the smallest stress, because that is the path of least resistance that we have. So a hydraulic fracture will be perpendicular to the smallest principal stress, the least principal stress. So that is my path of least resistance. Don't tell me, if I ask you this question, you have to tell me it is perpendicular to the minimum stress. is perpendicular to minimum stress, not parallel to the highest stress. They are mathematically they are different. The answer would be when I asked what's the orientation, it is always perpendicular to the minimum principal stress. So let's look at stresses and basic theory. This is very famous graph being published by so many different people, so I just took it from, I think the first company that published it was GMI, although when I was in Halliburton, we used something very, very similar to that. So here, I'm going to look at different types of faults, and that will be an indication of the regime, the stress regime that we've got. So if I have a stress regime in what I'm looking at, the formation I'm looking at, where the vertical stress is the highest, and then you have the maximum horizontal stress, and then you have the minimum horizontal stress. If you have a fault, then the fault will go. I always like to show it with the illustration, but anyway, this side of the fault will go down. It goes down because you have very high stress pushing into it. So if I fracture this formation, if I have this situation, which I'm going to call it normal stress regime. If I fracture this situation, what kind of fracture do you get? Well, the fracture has to be perpendicular to the smallest stress, and here the smallest stress is the horizontal stress, SH min. So that tells me that the fracture will be vertical, and it is perpendicular to SH min. So I'm going to jump to the reverse stress regime, the last one. Here, this is not as common. Usually, the normal stress regime is the common regime. You see it in most situations for formations that are deeper than 1,500 feet or so, which is the cases that we usually fracture. They're always, some are shallower than that, but usually it's deeper formation, and what you see is normal stress. And when I say usually, there is always exceptions to the rules. So let's go back to go down now to reverse stress regime. Well, reverse stress regime, when your vertical stress is the smallest. So your maximum horizontal stress is the highest, then followed by minimum horizontal stress, followed by the vertical stress. So if I fracture a formation like this, what do I see? Well, I'm going to see a horizontal fracture. Do you see it sometimes? Yes, it could happen. As we are going to look at what causes stresses in underground formation, I've seen it not very often, but I've seen it sometime, especially near mountains. I've seen a case like this in South America, and unfortunately we never got the data. I wanted to get the data very badly because it was a very interesting, different situation than what you see, and it has its signature when you run testing and stuff and logging. You see a different signature of the horizontal fracture, so you don't see that very often. Now in the middle, I have a strike-slip situation. A strike-slip situation, and when the vertical stress is in the middle. So the highest stress is the HS max, the smallest stress is the SH min. The minimum horizontal stress is the smallest. So if I fracture it here, what happens? Well, what happens is we already know that that a fracture is perpendicular to minimum horizontal stress or minimum stress. So the minimum stress is a horizontal, so I have a vertical fracture perpendicular to my minimum stress. However, situation like this, you could have a problem. One is many times it becomes a T-shaped fracture. It hits the boundaries between layers, and you end up having a T-shaped. So you have a horizontal part of the fracture, and that when this happens, it will cause all kinds of issues during the hydraulic fracturing. Another big issue that we are not going to get into is during drilling, because now especially if you plan to eventually drill a horizontal well, as the well is deviated, you need, because as we say, is deviation, your deviation from vertical and the inclination from north or from your stresses. So you could have a lot of problem during drilling. We're not going to get into that, but this is a very important issue. So if you suspected that you have a strike-slip situation, you have to test the formation, you have to test it, because it's important to know which regime you are in. That gets you design the drilling path and the fracturing later on. Years ago, we actually, a company spent a lot of money. We worked with them in order to figure out whether it was a strike slip or normal stress. Luckily for them, eventually after we ran all the testing, it was normal stress. So let us look at a couple of cases here kind of quickly. Here I have a fault. Well, is this normal stress? Usually when I teach, I ask a student to tell me, here I cannot see you. And so I'm going to tell you, here you can see this part here went lower. You see, this is a little higher. So that is normal stress regime. This is a similar situation. You see the fault here, and you see that the little man is working on it. You can see that this side, the right-hand side part of the formation dipped down. So this, at the time, it was normal stress regime. How about this one? If you look at it, and you look at it from far away, you can see as if the formation just slipped sideways. That's a strike slip situation. How about this? You see the fault here, and rock actually bent as if it is it's a soft tank, but under high pressure and the high temperature, even rock will turn around. That's the reason we see an anticline and all this geologic formation. So this is, you can see this right-hand side dropped below this right side, that the left-hand side part of the rock. That is reverse faulting. So this must have been, at the time it happened, must have been extremely deep. And not only deep, that's high pressure and high temperature, but also was exposed to some external, very high external forces that caused the horizontal stresses to be higher than the vertical stresses. We'll see why. So what causes all those stresses? We'll go through some of them, not all of them. The biggest one is the tectonic plates. Let us look at it. Then we'll talk about topography, the mountains, lateral variation of the thickness of earth, sometimes localized load, and it may be just the weight of the rock. Thermal stresses can be important also. We sometimes take advantage of this in the fracturing process. I will talk about it a little bit. So tectonic plates if I look at this map, and this map was created, as you can see at the bottom here, by Karlsruhe University. You know, when I hear that, it's like this because I spent one summer actually as a graduate student at Karlsruhe University, University of Karlsruhe. It's an interesting place, very strong technically. You look and you find the Earth is broken into pieces. You look at this, for example, you look at Africa is sitting on a tectonic plate that looks very much like Africa, only part of it is above water, the rest is underwater. South America is similar, North America is similar, Asia, Euro-Asia, it is in one tectonic plate. Actually, you can break the tectonic plates into, there is major ones, but you can break it into sub-major ones. I can tell you here in United States, you have this tectonic plates here, and it can cause earthquakes. And that's the reason for behind the earthquake in San Francisco back in 1905. Your tectonic plates here, you can see breaking through Iceland. We'll look at this in a second. So Earth is alive. Actually, people did not realize that there is such a thing as tectonic plates until the early 20th century. Someone wrote a paper on the subject, and people did not believe him. Because they thought it's just a coincidence that Africa and North and South America look the way they look. Till after Second World War, the exploration of bottom of the ocean revealed that there's actually this like a volcano type line here. And it was in this area, if you see around Indonesia, this is what caused the tsunami back in 2000 something, 2005, maybe around that time. But there was a huge tsunami that killed 250,000 people. And it was caused because of the tectonic plates, because tectonic plates, they keep moving. For example, the movement here across Iceland, it basically the Euro-Asian plate and the North American plate, they go away from one another about an inch per year. It sounds like it's very small amount, it's a very small number, but over millions of years, that becomes a huge distance. So here, what they did in Karlsruhe, they were trying to find stresses. So, for example, an area like here, South Africa, this is thick arrows. This is an indication of a strike-slip situation when you have arrows going into one another like that. If they are going away from one another like this red arrows, that tells me I have normal stresses. I usually give students a homework to go download another map of your area. In US, I ask them to download the map for United States and explain what the stresses that we have. Those are regional stresses. Does not mean that local stresses will be exactly the same. That is, we already found that a long time ago that this is not the case in South Texas, although it looks like you have some strike slip here, where many areas were actually normal stress, and the stress orientation changed across a fault. Okay, let's look. This is just showing part of the Alps is actually is from Africa, because you have the African plate and European Euro-Asian plate are colliding, and the African plate is basically going on top of the Euro-Asian plate. That causes a lot of stresses. If you go back to this map and you see these huge stresses near the Himalayas, near any time you have a mountain. In Iceland, I downloaded this map from Google. You can see in one side, this is Europe. On the other side, this is North America. And so there is a bridge that you will be, you go from one side to another. You are crossing from the Euro-Asian plate to North American plate. And this distance keeps increasing. So in lifetime of a person, it goes away by 6 feet. And the way it happens, and that's the reason behind the tsunami, is one tectonic plate may be going under the other or getting separated. And what happened in the tsunami is, although we say it moved about 1 inch per year, does not mean it is going very smoothly. In the tsunami, there was no movement for a long time, and then it jumped. It built up very high stress, and basically one plate jumped over the other. It moved the estimation is 25 feet. It moved the water, although it may not. If you're sitting in the top of the water here in a boat, you don't really feel it very much. But as it comes closer to the shore, it goes from inches into many feet, and so it has catastrophic effect. And that's what it causes a lot of stress. Another, the thinning of Earth, basically the lithosphere. You look at, I have to give you an example of the Gulf of Mexico is getting thinner and thinner, so the stresses change. So you find that your minimum stress, if you are here near New Orleans, your minimum stress is like this, and your fracture is perpendicular to it. If you are in Mexico, the minimum stress in different direction, and the fracture is perpendicular to it. So does not mean that in the Gulf, the orientation is the same everywhere. So that is one reason people will have to test the formation to tell the orientation of stresses and magnitude of stresses. We'll talk about ways to do that next week. Localized loads like salt domes. So you have salt domes. Salt domes is under the high pressure and temperature, it flows. Salt will, although it may be hard when you take it to the surface, but on downhole it flows. The same thing with chalk. We have fractured the chalk formation, and if you look at chalk in the surface, when you take a sample, the surface is very hard, but downhole flows like, not exactly like fluid, but it creeps very much. So salt dome, it moves and it can cause stresses. So I don't have a graph for it, but if you go downhole, if you take a cross section, you can see it's pushing the formation up, and the oil will be trapped between the salt dome and the formation, because salt dome has basically zero permeability. So you drill on the side of the salt dome. So as you move around, the orientation of fractures will change, because orientation of stresses will change. Gravitational stress is interesting. You basically, it is weight of the rock. So your vertical stress in most cases, it is nothing but the weight of the rock. So it is, if I have various formation between surface and downhole, all you're doing is you're integrating that weight. So it is, and easy equation to do this integration. If it is, you can break it into various layers and add the stresses. If you do not know the value, most people will say, okay, what is my specific gravity of sandstone? If you remember, if you multiply the specific gravity by 0.433, you get your gradient. And so that gradient for sandstone is about 1 to 1.1 psi per foot. And so if I do not know anything about the formation, I'm just making a very quick estimate. I would say, okay, my formation is 5,000 feet deep multiplied by 1 psi or 1.1 psi per foot. Then my vertical stress should be between 5,000 to 5,500 psi. So that is an easy way to do it. If I give you a formation and said, okay, we have all this formation, here is the specific gravity of each rock. Some of them may be 3.6, maybe less, multiplied by 0.433. So if it is a sandstone, is 2.65 then approximately. So 2.65 times 0.433 is about 1.1 psi per foot or so. But if I give you information, you need to do it correctly. You can do it easily. And that's what exactly what log would do when they calculate stress for you. All they are doing is calculating the vertical stress. We'll talk in a minute about calculating the horizontal stress. So you're integrating. If I'm in water, then part of it is water. You can see the equation. Part of it is in water, part of it in the rock. So in water, the specific gravity is 1 times 0.433. So I have 0.433 psi per foot. So if I'm drilling in offshore well and water depth is let's say 2,500 feet, which is not really that deep in what we do now. So that will be 2,500 times 0.433. So that's almost 1,000 psi, or a little higher than 1,000 psi, and plus the weight of the rock. So let's look at the mechanical properties, the Young's modulus and Poisson's ratio, and Bart's constant. So we'll do it experimentally, like what we have done that personally. We've done that in the lab many times, and we do it also from logs. So if I do it in the lab, and there is a difference between the two, and the difference is kind of important. If I do it in the lab, I get a plug or a core, and apply stress. I keep varying that stress, the force. I increase the force, so I'm increasing the stress, and I build. Then I take the change in height of that plug and divide it by the total length. That gives me the stress. So delta L over L is the strain. The force divided by the area is my stress, and draw this straight line, and the slope of the straight line is my Young's modulus. Okay, Young's modulus for a hard sandstone maybe 5, 6, 7 million psi. This is the stress is in psi. The strain is unitless, is dimensionless parameter because it's length divided by length. So if I have hard sandstone, maybe 5, 6 million, we'll give you a table later on about the values. So 5, 6 million psi. If you work in industry, most people you say 5 or 6, meaning 5 or 6 million, not just the 5 or 6, but so 5, 6 million psi, and I'm talking in English units. If you work with metric units, then you need to translate that. And the stiffer the rock is, the higher the slope. So if I go into softer rock, you get smaller, the slope is smaller, so it's smaller Young's modulus. Okay. Now, Poisson's ratio, let's talk about Poisson's ratio, then we'll give a table. If I repeat the same, if I'm running this experiment again, and I'm applying this force, not only I'm measuring the change in strain, I'm getting, this rock is getting wider. So there is axial strain, which is delta L over L, but there's also lateral strain, which is the change in radius divided by radius, or you can call it change of diameter divided by diameter. And if I take the ratio of the lateral strain divided by the axial strain, that gives me what we call Poisson's ratio. Poisson was famous mathematician, French mathematician back in many years ago, in 1700s or so. You can see this. That ratio has to be less than 0.5 for a rock. If you're running these experiments on a rock, that ratio, that Poisson's ratio, is definitely less than 0.5. If I give you a problem, and I've done that before, trick the students. If I give you a problem and you end up calculating Poisson's ratio 0.5 or larger, unless I wrote the problem wrong, which is very unlikely, or you made a mistake, which is probably the case. It happened in an exam that I've given. And so I had to tell the students, hey, you calculate a value 0.5 or higher for Poisson's ratio, you are making a mistake. You need to look back into it. And why is that? 0.5 means that the rock cannot carry any load. So it's almost like fluid, like liquid. So obviously that is not the case. And I used to give a problem for students to understand that better. Okay. Then you have shear modulus. Shear modulus is basically the formation. If you apply force, and then your shear force, then it will deform the rock by an angle theta. And shear stress, shear modulus would be shear stress divided by this angle in radians, not in degrees. And you know the pi is basically 180 degrees. Okay, but you can calculate shear modulus. It is related to Young's modulus and Poisson's ratio. So if you know Young's modulus and Poisson's ratio, you can calculate shear modulus. It's interesting that they are all things are related to one another. Young's modulus and Poisson's ratio are independent variables. I'm falling behind very much, but so it's probably another half an hour or so. Bulk modulus is actually the inverse of compressibility. So if I apply stress around the rock, the volume gets smaller. So it is essentially 1 over compressibility, except that we call it, in rocks we call it bulk modulus. And again, its bulk modulus is related to Young's modulus and Poisson's ratio. So here is the relationship between one and the other in this table. That's assuming isotropic material. The values you have, you can see Young's modulus for granite, it can be 10 million, and this all in psi. In shale, it may be shale. You can have soft shale and hard shale. Most shales are not as hard. This is here we're talking about hard shale that is almost as high as rock. But steel would be 20 to 30 million. Cold seam is 0.3 million. Let's look at sandstone. Sandstone can get higher than 4 million. With Poisson's ratio, it's usually higher than 0, but Poisson's ratio has to be less than 0.5. Usually, in what we deal with, the confining shale usually is softer than sandstone. And this is a very interesting parameter. We are going to look at it in a minute. But let me first talk about the parameters we looked at so far: Young's modulus and Poisson's ratio, shear modulus. This we call them static measurements. Dynamic measurements is where you are vibrating the grains. So you want to vibrate the grains. What you do is you apply sonic wave. Sonic wave will vibrate the grains, and your vibration happens either longitudinal, as you can see in this picture, or transverse. So if you are in one place, and you can see the reference of this slide. I find it like an interesting slide. And so you can see there is vibration going longitudinal or transverse. So if I apply sonic wave, the wave either will go compressional wave, so it moves from one place to another. So if I have a source in one, say at the bottom of the well, and I have a receiver a little higher, I can hear the compressional wave coming in, and then I hear the shear wave coming after it. Okay, and so I hear the compressional, then I hear the shear wave. The difference, the difference in time or in velocity of the two is an indication of Poisson's ratio. So here, if I'm listening to it, I take the DTS, which is shear divided by compressional. This is taking longer time to arrive than the compressional wave. The shear wave taking longer time to arrive. I divide them one another, square it, take 1/2 minus 1, and do this. Use this equation. I can calculate Poisson's ratio, and that is the way logs actually calculate Poisson's ratio. And then in a minute we'll see how they calculate the stress out of that, because you run sonic log, you're getting density of the rock, so you can calculate the vertical stress. If you integrate the whole thing, you get the vertical stress. If I'm also doing sonic log, and I have to have enough distance between the transmission and the receiver in order to be able to see the compressional and shear wave distinctly from one another. Once I get the Poisson's ratio, then I can get shear modulus. Here is a simple equation where A is a constant here, and from there I can calculate Young's modulus, and you will be in business. So you can do it. You can do it with logs. Okay? Or if you have velocity, here is the shear wave and the compressional wave, the V sub P. So before we leave this area, okay, let's say I calculated Young's modulus and Poisson's ratio here from a log, and I also calculated from any lab experiments, which is static. So which one would I use? Are they equal? The first question should we have an agreement? Should these two parameters, whether static or dynamic, be equal? Well, probably not. There are two different types of measurements. One is static and one dynamic, and they will be different. Which one is larger depends on a lot of parameters. So we're not going to get into that. But which one would you use? Most people are going to say dynamic, and the answer is no. It is use static values in designing the fracture. Why is that? Well, the dynamic values is actually you are vibrating the grain, but when you look at your fracture, although the fracture is obviously a dynamic process, but it is not depending on vibrating the grain, is actually pushing the rock very much like what you do in experiment. And so what we would do is you develop a relationship between the dynamic and the static properties in your formation. It's easier to run logs. So you run the logs, you take the values, and boom, through your correlation between static and dynamic, you get the static and use that in designing the fracture. Okay, I may have said it a little fast, so you may want to listen to the game. So here is the stresses. Now, this area is a little dry, I have to admit, but it's important to understand. So now what stress would you use? Well, the stresses that you have, the total stress is carried by both the grains, sandy grains, and by the fluid. Okay, so and what is affecting the propagation or sanding or collapse of the rock is the effective stress, not the total stress. Effective because the stress is being carried by both the grains and by pore pressure. The first attempt to do that, to look at it, was Terzaki's effective stress. He said, hey, what is being carried by the grains is you just take the total stress and subtract out of it your pore pressure. However, people found out later on that pore pressure may not be 100% effective in carrying that stress because it moves out as you press it, it moves out. So and they say, well, there is a factor here that it is usually less than 1, which will bite coefficient. So rather than assuming it's 100% efficient, using partly efficient. So that's about constant anywhere between 0.7 to 1. It depends. Most people will probably use about 0.9 or so. But it is important to measure that parameters, especially if you're going to look at sanding. That is very important to do. So you can see in some situation your bite constant for Ottawa sand, porosity, if it is dry, is 0.33. You can see that's in megapascal. If you want to relate to it, this is megapascal is 10 atmospheres. So you multiply any of those numbers by about 145. 1 atmosphere is 0.1 megapascal. And so you can see there is, depending on the rock, it may be up to 0.9, and in some rocks it may be down less than 0.5. So it's important to test the rock. You can only find it by testing. You test the rock and you find what batch constant, batch coefficient you have, because that's going to affect your sanding issue. So we've done that. This is just a table to give you specific gravity of different material in case important in case you get a problem on calculating that stress. So fresh water is 1. This your specific gravity is dimensionless. So to get the stress downhole is the depth, the integration of the depth times specific gravity time 0.433, which is the gradient of fresh water. So in case of quartz is about 2.65, so 0.433 times 2.65, it gives you whatever value is a little bit more than 1 psi per foot. Now, without going into, let me look at the first equation. I usually we go through the derivation of this equation, which is very easy to do. And my advice is you go, if you Google it, you'll find the derivation. Derivation is very simple. Basically, all you're saying is that when we calculate Poisson's ratio, we're saying it's unconfined, and we calculate how much lateral strain you have. But if that rock, where you're applying stress, is part of a huge formation, then it doesn't have room to expand. Then it's applying stress. So Poisson's ratio also is saying when I apply stress vertically, part of it is going to transfer horizontally. And so if I apply this concept, then I can say when I apply effective stress vertically, which is sigma V dash, there will be sigma H dash. There will be a horizontal stress, effective horizontal stress moving sideways. The relationship between the two is based on Poisson's ratio. Okay, and so you can see Poisson's ratio has to be less than 0.5, because if Poisson's ratio is 0.5, that's saying the stress is transferred horizontally 100%, that the rock cannot carry any stress, which obviously that is false. So if the rock can carry some stress, then Poisson's ratio has to be less than 0.5. In sandstone, it may be 0.35 or so. So you can look at it and say 0.35 divided by 0.65. So it's a little bit more than half the effective vertical stress. Okay. In case of shale, if it's softer shale, it may be 0.4, a little higher than 0.4, not much higher. Sandstone maybe even less than 0.35, maybe 0.3. So you can see that this is the reason that the softer shale will have higher horizontal stress than hard rock, sandstone. And this, as we are going to talk about next week, this provide us with some confinement of hydraulic fracturing. So nature was nice to fracturing to the oil industry to create fractures that are somewhat confined. We'll talk about more about that next week. And so here I'm just giving you this equation that I usually ask students to derive. You can see in the first equation is the relationship that very easy to derive. You may want to Google it. I may add the derivation to the presentation that will put it in ResearchGate, and we send you a link of the last week presentation. You're going to receive another link for this week's presentation. Then if I substitute the definition of the effective stress, I end getting here an equation relating the total horizontal stress to the total vertical stress, and obviously pore pressure will appear, and also alpha will appear. If we're in class, I would have asked you if you remember what alpha is. It is Bytes constant. In situ stress orientation is very important. There is multiple techniques to calculate it. That will, let us wait till when we talk about testing next week. There's a lot of ways to do it. And next week we'll talk about the microfrac testing, I may add something, but I was not planning on it. But an elastic strain relaxation, this is something that's very interesting that we have done previously. We'll talk about it next week. We probably will not talk about tiltimeters. It's been used before. It's very interesting technique, but we may be able to. Then people will use well testing and doing it. Geological rules of thumb. I have personally used that. We work with a company, and the company was not they really did not want to run any testing. Say, well, can you guess what it would be from our geologic map? I looked at it and they said, yes, yeah, we can do that. You look at it, it was an anticline. There was already long natural fractures. There was faults in the formation. So it would be parallel to the hydraulic fracture. Most probably would be parallel to this fault. So you follow the anticline. And so that is one way of doing it. Let me look at the effect of drilling a well bore, because this is something I want to cover before we. It is fairly important to understand the breakdown of a well bore to create a fracture. So when you drill a well, I should have had a graph here. When I drill a well bore, I change all the stresses around that well bore. Okay. Many years ago, this equation was developed. When I say many, I'm talking about more than 100 years ago. You know, if you know, mathematics is more advanced than any other technology. People develop stuff in math that takes many years before it gets applied. So if I have a rock, and let me show you, basically I did that by hand a couple of days, or actually over the weekend. If I have drill a well bore like this, and the minimum stress is this way, the minimum horizontal stress, the maximum horizontal stress is in the other way, and I'm looking at the top of the well bore. So the vertical stress is going vertically into the picture. And I'm going to look at an angle of theta here. So I can look at any point in the reservoir, not inside the well bore. Any point inside this reservoir, this is the white area is my reservoir. And if I draw a straight line to the center of the well bore, I have this angle theta. So the stress at any point inside this reservoir is defined by these two equations. So sigma RR is whatever stress that is going perpendicular, going towards the center of the well bore. Sigma theta theta is the stress adjacent or tangential to the well bore, or parallel to that well bore. So you can see it is moving like a circle around this well bore. So this equation would describe, so now you know the definition of sigma h, sigma h max, and the theta. RW is the well bore radius, and the R is whatever distance you are away from that well bore, from the center of the well bore. So I'm going to do it just mentally here, rather than, usually it would be, I want you to, it may be a good exercise for you to eventually sit down with a piece of paper. I'm going to do it very quickly here. So the first question here is, what is sigma RR at the well bore? without looking at the equation. Well, sigma RR at the wellbore, if the wellbore is stable, should be 0. So let us substitute here. So at the wellbore, RW is equal R. So this is 1. 1 minus 1 is 0. So the first term disappears. And here was 1 minus 4 times 1 plus 3 times 1. So that is again 1 minus 4 plus 3. That is 0. So the second term is 0. So sigma RR at the wellbore is 0 regardless of theta. So that's now I have a stable well. If it is not stable, we'll find out later on. Maybe next week we'll talk about testing. We'll see other situations. So sigma R is regardless of theta at the wellbore, it is 0. That sounds very good. So now let us look at sigma theta theta, which is tangential to the wellbore. So at the wellbore, RW square divided by R, well, R is equal to RW, then this is 1. 1 plus 1 is 2. 2 here cancels out, so I end up having with sigma H plus sigma H max minus this second term. I'm going to do it now for theta equals 0 and theta equal 90 degrees. Okay, so everyone get a piece of paper and follow what I'm saying. So at R equal RW, so I have sigma H plus sigma H max minus, this is 1 plus 3 is 4, then it becomes a minus. I'm going to open parentheses, 2 sigma H minus 2 sigma H max time cosine. If I'm at 0, cosine 0 is 1. So when I put this all together, it ends being 3 sigma H max minus sigma H min, right? Okay. Now I'm going to do the same thing again, except I'm going to put theta of pi over 2, 90 degrees. So pi over 2 times 2, that's pi, that's 180 degrees. What is cosine 180 degrees? I hope you remember it is minus 1. So if I put that, now multiply that second quantity by minus 1, I will find out at 90 degrees, the equation is fairly similar. It is sigma 3 sigma H min minus sigma H max. Okay? Remember that, because this equation, I will be asking you if you know anything about hydraulic fraction, you remember the CFD definition and you remember this equation too, as well as the equation for Poisson's ratio, the relationship between the vertical and minimum horizontal stress. There's 3 equations you need to remember. So if I look in here, I find out the sigma RR at theta equal to 0 is 3 sigma H max minus sigma H min. And at 90 degrees, which would be vertical here, the sigma theta would be vertical. It is 3 sigma H min minus sigma H max. Now, if I'm ballooning, if I'm injecting fluid and I'm getting this well to expand, to get a little bigger, where would it break? It would break at this point where it has the smallest stress, because what I find out that this would be the smallest stress here and the high, talk about tangential stress, and this is the highest tangential stress there. So fracture is going to break here and propagate perpendicular to minimum stress, which that's the way it should happen. I look at the breakdown pressure, and it looks something like that. So sigma RR at the wellbore, regardless of where you are, this is sigma RR, is 0. And when you go away, it goes back to the far field stress. Sigma theta theta depends on your orientation. So if I have a graph like this, which sometimes people call it hoop stress. So hoop stress, here is the largest, here is the smallest. So So if I'm ballooning the fracture, it will break at the smallest value. There are a lot more to it because as you fracture the well, you change the stress regime. So here I'm saying this is wellbore that has not been fractured yet. So I apply stress, it should look something like this. If I increase the stress, eventually it will break at theta equal 90 degrees. It's in here, like what we show. So the fracture will propagate this way, perpendicular to minimum stress. How about breakdown? Have you ever looked at a formation and you notice it's breaking down? Well, when it breaks down is under compression. So actually, breakdown will happen in this orientation because now I have very high maximum stress. It's causing the formation and lowering the pressure inside the wellbore very much that you have a breakdown here and here. Then if I look at a breakdown, I know immediately that the minimum stress is in the other direction. The minimum stress this way, so the fracture is in the other direction. So how to take care of it is you increase the weight of the mud. And here is the equation considering the pore pressure and the depletion of the formation. So here I have wellbore pressure and I have pore pressure, and obviously here you'll be considering Bright's constant. So what equation you would remember? You wanna remember? Let's go back to this equation. You want to remember not this whole equation, but you want to remember the 3 sigma max minus sigma h, because that appears very much. You want to make it more accurate, you add the tensile strength to it. You want to remember CFD, and you want to remember the Poisson's ratio. So let us entertain a couple of questions. Again, I'm going to put this presentation on ResearchGate. We'll send the link to Dr. El-Garhi, who will communicate with you. But you don't actually even need the link. If you know what ResearchGate, and you can get on it and you can download anything you want, assuming it isn't there. I've sent also, Dr. El-Garhi will send you a link to some write-up I did. It's a long time ago, in mid-90s, early to mid-90s. However, it is still a very good write-up. It's mostly for fracturing horizontal wells, and I would suggest that you read it for your own enjoyment. Anyway, let's entertain a couple of questions.
Okay, so thank you, Dr. Soliman, for this informative session. Now we will begin by addressing the questions. So the first question is that should we drill the horizontal wells in the direction of minimum horizontal stress direction, and why?
That's a good question. Actually, drilling a well in the direction of minimum stress, we found out if you have normal stress regime, actually this is the most stable situation you've got. So, second, we don't have, I don't have a presentation on that. Well, I do have in my computer, but not in here. People always talk about what is the optimum or the best way to deplete a formation. You want to drill horizontal well and fracture it, usually in very tight formation. And the best way to do that in a tight formation is to create multiple fractures in that horizontal wells. If we look at history of what we have done, we started, and the first fracture of the horizontal well was in late 80s. Actually, I do have a paper on the subject you can download from SPE that I wrote back and presented it in 88, and it was published in 1990. Well, I can't send you a link of it because SPE owns the copyright. So you have to download it from SPE. And so we used to talk about 4 to 6 wells. Now we fracture not even 10 or 20, sometimes 100 fractures in one horizontal well because the formation is extremely tight. You can't, you can do that only with horizontal well where you create multiple fractures. If we have time at the end, I will show you. Actually, I do have a nice presentation on that we did 8-10 years ago. I may put it also in ResearchGate because it is my presentation. I cannot put papers, but I would put it in ResearchGate. Look at it. It's a very interesting presentation, and it deals only with fracturing horizontal wells. And that usually I used to cover it. It's only mostly about fluid flow, and it used to take me about 3 hours to present. But we'll put the presentation. You may wanna look at it.
Okay, great.
Sometimes in the future, we may present it to the group in the distant future. Go ahead.
Okay, great. Thank you. And the second question is it possible to see hydraulic fractures in real life? And if yes, is there any real example for that?
You see it real life?
Yes, I think he means if it's visible, like to see it in the naked eye.
No, not visible.
Horizontal
But
fractures.
let me say something about that. We have many years ago, when I was in the Halliburton company, Halliburton developed a tool. I was involved in it. There was a lot of people were involved in that specific tool, and it was a joint project between Halliburton and Total, and it was called the tool, THE, for Total Halliburton extensometer. And basically, we worked on myself and my group. We worked on the rock mechanics side of it, and there was other groups working on the electrical part, another group working on mechanical part, where you go in and you inject the fluid and you balloon the well, so you don't observe it by eye, but you observe the behavior of ballooning of the fraction of the well bore, and eventually you observe or measure the behavior of the fracturing process and the widening of the fracture.
Dr. Soliman, I believe the question means instead of having vertical fracture, he's talking about horizontal fracture. Is it a real cases that we see horizontal fractures in real life?
Did he say horizontal fracture? Or?
Yes, horizontal fractures. Yes.
Well, I have seen cases. At least there was one very clear case where it was a horizontal fracture. I have another case that you don't. Let's not say see, but observe the behavior of horizontal fracture. We've seen that. It's not very common, but we have seen it. Yes, it can be done in a vertical well. You see horizontal fractures.
Okay, great. Thank you. And the last question for today, can we use the dynamic Young's modulus to design a hydraulic fracturing operation or job without converting it to static Young's modulus?
The answer is no. You need to convert it to the static values. There are many people have written, there have been a lot of correlations. You have to build the correlation based on your reservoir. So many people have done that. You can't just, there is no general relationship between the two. It has to be developed for a reservoir or a basin.
Okay. So thank you, Dr. Soliman, for joining us this afternoon, and we were a pleasure to have you today. And I just want to highlight that this session was been recorded and it will be uploaded soon on BioPetra's YouTube channel. And also for those who are considering to join this course, they already missed a quiz. However, they can still join, yet they should pass the 3 remaining quizzes and do the final exam. And for those who already joined, and please continue doing the quizzes and do the final exam. Now, best of luck, and thank you again, Dr. Soliman, and have a nice day, and see you in future webinars. Thank you.
All right. Bye, everybody.